Hi, good afternoon. This is Mr. Cassidy, and I'll be going over lesson 12.1, angles of triangles. So this is a pretty straightforward lesson, and yeah, let's get into it. First, let me get my pointer tools. Nope, not that. Here we are. And let me test it. Awesome. Okay, so let's begin. So first, you'll need these definitions, and you may just need them out. If you aren't familiar with them, they're pretty straightforward. Scalene triangles means there's no congruent signs. If I mark that, I would use one mark on one side, two marks on another side, and three marks on another side. That means all three sides are not the same length. Isosceles, two sides are the same congruent lengths. Equilateral, all three sides are congruent. An acute triangle means all three angles are less than 90 degrees. A right triangle has one 90-degree angle. An obtuse triangle has one obtuse or greater than 90-degree angle. And an equal angular triangle means three congruent angles. All right, moving right on. So the first kinds of problems you might face are just classify the triangular shape of the support beams in the diagram by its angles, sides, and measuring the angles. You don't really need to measure the angles. You just need to look at the side markings. I see that there are two congruent sides here. So that is an isosceles triangle. Now, if I measured this, I could take out my protractor, look at the degrees here, and be like, oh, it's 55 degrees at this corner. But we don't need to worry too much about that. But you can just look at these. If we look at the three corners, all three corners are acute. They're definitely less than 90 degrees, and so we'd call it an acute isosceles triangle. Typically, when we're naming a triangle, we have one word that refers to the kinds of angles and one word that refers to the sides. So, by naming the angles acute and isosceles, we've named both parts of the triangle. So it's a little trickier when we have a triangle on the coordinate plane, but I do have a trick for this. We have to decide, is this acute, isosceles? Let's start with the sides. So to decide which kind of a triangle it is, we need to decide the side lengths here. Now there's two ways you could do it. One way is the distance formula. You could do the distance, say, between PQ. You would do PQ here, and you would use that huge formula, right, where you do x2 minus x1 squared plus y2 minus y1 squared minus y1 squared, 1 squared, and then you take the square root of all that. That will give you the distance, and so then you would repeat that with each of the three sides to find their lengths. But here's my trick. You can compare the lengths just by making a right triangle on the outside of the side. So I'm drawing the right triangle right here between P and Q, and that's my right angle because it's on a grid line. And I notice that that is one square up and 1, 2, 3, 4, 5, 6, 7 squares over. So all I need to do is really compare that outside with the other triangles on the outside. So here, this is a 2 down. Sorry, let me try to make that a little cleaner. 2 down and 1 over, 2 and 1. So I know that this side definitely does not equal this side. And let's take a look at the last one. Now, if I get the same little ratio, sort of the rise over run, or the same ratio of the two legs, if I get the same exact two legs, then I know that the sides are equal. So in this case, it would be 3 rising, and running is 1, 2, 3, 4, 5, 6. 6, well, that doesn't match a 1 by 7 triangle. So I know that this side's not equal, so therefore this is scalene. Now, how about angles? How do we know? Really, it could be an acute triangle. Really what we're looking for is it a right triangle or not? I can tell that this does not look like this corner here at corner P. That does not look like a right angle, but this corner O might be a right triangle. So what I want to do is I want to compare the slopes of those two lines. Now, luckily, I've already done the outside triangles here. So I'm going to do rise over run and then puff, puff, positive or nice negative. So the rise over run from P to O, PO's slope is rising 2, running 1, but it's going down, nice negative, right? So I would put a negative 2 over 1. And then I compare that to the slope of OQ, and the slope of OQ is going up 3 and over 6. So up 3 over 6, and let me simplify that. Well, that is 1/2. And actually notice that's the negative reciprocal of each other. So those are perpendicular lines. Negative 2 over 1 flipped over is the same as 1 over 2. That means that those lines are perpendicular. I could draw a right angle here. So I know this is a scalene right triangle. Okay. Now here's all that work. If you actually wanted to do the distance formula, you would do distance formula on all the side lengths and get them, but notice I showed you already the easier way to do that. Then you could actually use slope formula, but again, it's easier to draw triangles on the outside, right triangles, to find the rise over run of each of those line segments and also compare those right triangles to find the side lengths. We arrive at the same conclusion either way. I just think that other way, my way, is a little easier. So let's move on. However, this, not to discount this wonderful algebra right here. I think it's to be applauded, all this work, but there is an easier way. All right, let's carry on. So go and practice problems 1 through 3. Classify each triangle by its sides and by measuring its angles. Go ahead and pause if you'd like to try it yourself. And here's your answers. The first is an obtuse scalene. You can tell that Q is an obtuse angle. It's bigger than 90 degrees. And scalene because none of these sides really match. Next one. Problem 2 is probably a right scalene. Now, if you got that wrong, I don't blame you. This isn't marked, so we can't 100% tell without using a protractor. So no worries. And last, we've got an acute isosceles because we have two sides that are the same. All right. How about classify triangle ABC by its sides? So you're going to need to graph this. ABC, I'll do a rough graph of it here. 6, 6, somewhere about here. 9, 3, here. And 2, 2, somewhere about here. So graph it. Again, try my technique of doing the outer triangles to compare the side lengths and the angles, finding the slope to see if anything is a 90-degree angle. And here's the answer. I'm just going to, since I've gone over this type of problem, I'm just going to give you the answer. If you graph it, there's the actual one. It's right scalene. We can see that this is a right because the rise over run right here is the negative reciprocal of this rise over run. Okay? But if we do that outside triangles here, we see that none of them really match up. Okay, let's carry on. So finding angle measures of triangles. When the sides of a polygon are extended, other angles are formed. Inside the polygon is interior, and outside the polygon, if you extend those rays, are exterior. All right. Now, the first main theorem we get is the triangle sum theorem. Just means if you add up the three corners of the inside of a triangle, we get 180 degrees. And we'll be using that. Now, there is a proof of that. The way to prove it, and I'm not going to spend too long on this proof, but you may want to refer to it somewhere around lesson 3 this chapter, because there are some proofs this chapter. However, guys, we're on chapter 12, last chapter of our book. We made it. So here we've got the triangle sum theorem. First, we draw line D, which is parallel to line C, and so we're actually given that that is the case. I believe I've forgot. Oh, sorry, parallel postulate. We can draw a parallel line to any other line that exists. And so since AC is parallel, we can have a point B and we can add a point D, and we can make that line parallel simply because there has to be a parallel line that's parallel to any given line. So next, we're going to do part 2B, part 2, 3, and 4. We're going to show that the measures of the inside equals 180 degrees by first showing which angles are congruent. So first, we can do measure of angle 4, 2, and 5. That means this is equal to 180. Because of the angle addition postulate, we can add these up to get the total degrees and the definition of a straight angle. This is a straight angle because it's formed on a straight line. Next, congruencies. Well, angle 1 has to be congruent with angle 4. Let me go and mark that with 2 arcs here. And why? Well, if these are parallel, if these lines are parallel, those are alternate. Alternate, again, means either side of the transversal. And here's our transversal. Alternate interior angles. So that means the alternate interior angles theorem. And again, knowing the word theorem versus postulate, not too big of a deal. If you called it postulate, that's fine. Really, we're just looking for that's what alternate interior angles are. And then we also have that angle 3, I'll use 3 arcs here, has to be equivalent with angle 5, has to be congruent. And again, that's because of alternate interior angles. So now we can use substitution. And, the definition of congruent angles. This is sort of that in-between step, just saying that the measurements here, if they're congruent, then the measurements are equal. So now we can talk about actual measurements, and we add up those measurements with substitution. And we've substituted, instead of talking about angle 4, we switched it with angle 1. And then instead of talking about angle 5 adding up to 180, we switched it with angle 3. So basically, we've substituted both of these because of the, because of substitution property, but after we proved that they were congruent using the alternate interior angles theorem. All right, carrying right on. The exterior angle theorem. Again, all of my notes on here, this is really just for food for thought. It's not something I want you to take a ton of notes on right now, but you may want to come back to this as we get into lesson 3 in this chapter later. Okay, exterior angle theorem is just saying this. If we draw an exterior angle, and it sort of is based on that last theorem, this angle 1 has to equal angle B plus angle A, the two other interior opposite angles. So angle 1 equals angle A plus angle B. And why is that? Well, because if I talk about this corner here, notice that this corner plus this equals 180. This corner here inside the interior angle, angle C, plus angle 1 equals 180. And this angle at C plus B and A equals 180. So we can sort of substitute angle A and B equal angle 1. So finding an angle measure. Here's a typical problem in this lesson. First, we need to solve for x, and then our problem is asking us to find the measure of JKM. That means JKM. This is what we actually want. We want this arc. So to find this, we remember that alternate angle theorem. We can do 2x minus 5 equals x plus 70. And so that's just going to take some algebra. 2x minus 5 equals x plus 70 because of the alternate or the exterior angle theorem. So I'm going to go ahead and solve for x by subtracting it on both sides. X minus 5 equals 70. And then I'm going to add 5 and get x equals 75. Now that I've found x is 75, I would plug that in here to get it. So 2 times 75 is 150. I'm just substituting for x with the number 75. Oh, I don't know how I lost all that. On for good. Well, we can at least use our brains here. 2x minus 5. I hope you guys got a good picture of that. And we get 150 minus 5 equals 145. Okay. So there may be some variations of that, like finding a different corner or a different angle, but it's all based on that rule. Okay. There it is. All right, and there's the explanation if you need to pause and check it out. Let's carry on. So go ahead and try out this problem. Find the measure of PQS. All right, and here's our answer. Measure of PQS is 145 degrees. Next, 5 and 6, we've got 2 exercises here. Again, find the measure of the exterior angle. Yeah, one should be pretty easy. It's 106 degrees. We just add the 2 interior opposite angles. And problem 6, find the measure of the exterior angle. Exterior angle is 8x minus 5 here. So we make that equal to the sum of these two. And we get 155 degrees when we plug that x back in. Okay, carrying on. Corollary to the theorem is a statement that can be proved easily using the theorem. The corollary is corollary to the triangle angle sum theorem is that the acute angles of a right triangle have to be complementary. And this sort of makes sense. We've got a right triangle here with one corner being 90 degrees. So because that's 90 degrees, if I know that the sum adds up to 180, that means A plus B here has to equal 90 degrees because that's 90 more to make the total sum of 180. There's a proof in your book in example 41 or exercise 41, page 593. I don't know if I'll sign it. We'll see. So here, find the measure of angle 1 and then find the measure of each acute angle. Just a little more practice. You've gotten 65 degrees for angle 1. How we should have solved is you should have done 5x minus 10 equals 40 plus 3x. Once you solve for x, let me do a little mental math here. 2x equals 50, x is 25. You have a few ways that you can then use that information. You could plug x in here and get 75 degrees is this corner. And then know that 40 plus 75 plus this corner equals 180. So in that case, 40 plus 75 equals 115. And from there, we can figure out 180 minus 115 is equal to 65 degrees, our answer. Here, find the measure of each acute angle. That means we do want two answers here. We want the measure of this angle and this angle. So here, first we know, based on the corollary to the triangle angle sum, that these two have to equal 90. So we could just write 3x minus 6. I added the x's in my head, equals 90. Solve for your x. And we know that one corner is 26 degrees and one is 64. All right, carrying on. Problem 7 is just a word problem, but it's based on all that stuff. In a right triangle, the measure of one acute angle is twice the sum of the measure of the other acute angle in 30. Find the measure of each acute angle in the right triangle. So it helps to draw this. Let me draw a right triangle. Here we are. And measure of one acute angle is twice the sum of the measure of the other acute angle in 30. So here, this one is going to be x, and this one, I don't have much room here, is twice the measure of that, the sum of that and 30. So now I can add these two corners together and put them equal to 90. In this case, 3x plus 30 equals 90. So when I subtract 30 and divide by 3, I get that x is equal to 20. And now that I've got this, I know that this corner is 20 degrees, and I need to plug that x in to get the other corner. 20 times 2 is 40, plus 30 is 70 degrees. Okay, and let me double check. 20 plus 70 is 90, and this is 90. That should make a good right triangle there. All right. Miss Carter got something different than me. That makes me doubt this question. Twice the sum. Oh, I see how she solved it. Now, I solved it a little different, but I think either interpretation could be valid. I'm guessing that what she did here, again, I'm sort of using her PowerPoint, is that 2x, she doubled 2x plus 30. And so what she got was 2x plus 60 plus x equals 90. I think either interpretation could be considered correct. In this case, you would get x is 10. In my case, I got x is 20. Let me reread the problem. Twice the sum of the measure of the other acute angle and 30. You know, it's tough without any comma or any kind of punctuation. It's tough to tell whether to make that a parentheses here or just apply the twice to the sum of the other measure. Well, I'll leave it up to you to decide who's right, me versus Miss Carter in today's showdown, and I'll email her with that add-on. All right, well, I thank your minds and your hearts. Hope you're doing well. And that's all for today. Let me figure out how to end my screencastify. Can you give me a second? I think I'm still live here.